Good morning, students. Today we'll discuss some important examples related to T0 and T1 spaces. So firstly, let us give an example of a topological space which is not a T0 space. So the first example is indiscrete topological space. Indiscrete topology is the topology consisting of the members phi and the set X. Here X is a set containing at least 2 points. Now we show that set X together with this topology that is not a T0 space. For the T0 space, we take a pair of distinct points x and y belonging to the set X. We are to show that there exists a neighborhood of X which also contains y. In that case, the space will not be T0 space. Now, in this topology, this X is the only neighborhood of the point X as well as point Y. It means we can say that every neighborhood of this point X contains Y, and every neighborhood of point Y that also contains X. So by definition of T0 space, we can say that X is not a T0 space. Now the second example of a space which is T0 space. Now we show that discrete topological space containing at least 2 points, that is a T0 space. So let us take X with topology tau2. Tau2 is a discrete topology on the set X. Discrete topology means the topology consisting of all the subsets of the set X. This topology is called discrete topology. Now let us take x and y belonging to the set X such that these 2 points are distinct points. Now singleton X, that is a subset of X and that also contains the point X. So we can say that this W, that is an open set containing the point X. So W is neighborhood of the point X. Now we can see that X and Y are distinct points, so Y does not belong to W. So we have obtained a neighborhood of X which does not contain the point Y. So we can say that the space X with topology tau2, that is T0 space. Now our next example is cofinite topological space. Cofinite topology, that is the collection of all those subsets of X which are either empty or their complement is finite. We show that this topological space is T0 space. Now let us take 2 points x and y belonging to the set X such that these 2 points are distinct points. Now if the set X is finite, in that case we already discussed that if the set X is finite, then this topology, cofinite topology, that is same as the discrete topology. And we already discussed discrete topological space, that is T0 space. So X will become T0 in this case. Now let us take the second case when X is infinite. Now let us take W is a set which denotes the complement of singleton Y. Now this set contains X, and also if you find the complement of W, that will be singleton Y which is finite. And if the complement of a set is finite, then by definition that set belongs to cofinite topology. So W is an open set which contains the point of X. So we can say that W is neighborhood of the point X. And also from here we can see that Y does not belong to this neighborhood. So we have obtained a neighborhood of X which does not contain the point Y. So by definition, cofinite topological space is T0 space. Now, the next example is co-countable topological space. Co-countable topology is denoted by the topology TOP4. This is the collection of all those subsets of X which are either empty or countable, or their complement is countable. X minus G is countable. Now, to show that this topological space is T0, let us take 2 points X and Y belonging to the set X, such that these 2 points are distinct points. Now, there are 2 possibilities. Either the set X is countable or uncountable. If X is countable, in that case, this topology is same as the discrete topology. And discrete topological space is T0. So we can say that X is T0. Now, let us take the second case when X is uncountable. Let us take W is the complement of singleton Y. Now, let us find the complement of W. Complement of W, that will be singleton Y, which is finite set, and every finite set is countable. So complement of W is countable. So by definition of this topology, if the complement of a set is countable, that set belongs to co-countable topology. So we can say that W is open set, and also X belongs to W. So W is neighborhood of the point X. And from here we can see that Y does not belong to W. So we have obtained a neighborhood of point X which does not contain the point Y. So by definition, this topological space is T0 space. Now, our next example is usual topological space, the set of real numbers with usual topology that also forms a T0 space. By definition, usual topology is the collection of all those subsets of R for which for every point X belonging to the set G, there exists an open interval AB such that X belongs to the existing interval that is contained in G. We show that usual topological space is T0. So let us take 2 distinct real numbers X and Y from the set of real numbers, and let us take epsilon is half of X minus Y mod. Now, because X and Y are distinct, so epsilon will be positive. Let us take W is the open interval X minus epsilon to X plus epsilon. Then this W, that is an open set containing the point X. So W is neighborhood of point X. Now we show that point Y does not belong to W. We prove it by contradiction. Let if possible the point Y belongs to the set W. Then the absolute difference of X and Y should be less than epsilon. But from this equation, X minus Y mod is 2 epsilon. It means from here 2 epsilon is less than epsilon. So we get 2 is less than 1, which is not possible. It means our assumption is wrong. So we can say that Y does not belong to W. So we have obtained a neighborhood of the point X which does not contain the point Y. So by definition, usual topological space is T0 space. Now, next we do the examples of the topological spaces which are T1 spaces. First example again of usual topological space. set of real numbers with usual topology, that is a T1 space. To show that this is T1 space, let us take 2 points x and y from the set of real numbers such that these 2 points are distinct. And let us take y is greater than x because they are distinct real numbers. So without any loss of generality, we can assume y is greater than x. And let us take epsilon is the half of the absolute difference of y with x. Here y is greater than x, so y minus x will be positive. So you can remove mod here. So epsilon will be y minus x by 2. Now let us take W an open interval containing the point x, which is given by x minus epsilon to x plus epsilon. Then this will be a neighborhood of point x. Similarly, we can take neighborhood of point y, which is the interval y minus epsilon to y plus epsilon. Now, because v is the neighborhood of point y, and we can see that x does not belong to v and y does not belong to w. So by definition, the usual topological space, that is T1 space, because we have obtained a neighborhood of point x which does not contain y and a neighborhood of y which does not contain the point x. Now, our next example is in discrete topological space. We show that in discrete topological space is not T1 space. In discrete topology consists of the members phi and x. If we take 2 distinct points x and y in this topological space, then x is the only neighborhood of point x as well as y. So we can say that there does not exist any neighborhood of the point x which does not contain y, or neither we have a neighborhood of y which does not contain point x. So by definition, the topological space is not T1 space. Now, our next example is discrete topological space. Discrete topological space consisting of at least 2 points, that is a T1 space. To show this, let us take 2 distinct points x and y belonging to set x, and let us take W is the set consisting of the point x and V is the set consisting of the point y. Now this is a subset of x containing the point x, so this is neighborhood of point x, and V is neighborhood of the point y. Now y does not belong to W and x does not belong to V. So we have obtained neighborhood of x which does not contain y and a neighborhood of y which does not contain x. So by definition, the topological space is T1 space. Now, our next example is cofinite topological space. Cofinite topological space is T1 space. To show this, let us take x and y, 2 distinct points from the set x. If x is finite, in that case, cofinite topology is same as the discrete topology, and discrete topological space is T1. So in this case, x is T1. Now let us take the second case when x is infinite. In that case, let us take W is the complement of singleton y and V is the complement of singleton x. Now this set W contains the point x and also its complement is finite. So this set is open. So W is neighborhood of point x. Similarly, V is the neighborhood of the point y. And we can see that V does not contain the point x and W does not contain the point y. So we have obtained a neighborhood W of the point x which does not contain y and a neighborhood V of the point y which does not contain x. So by definition, we can say that the set X together with cofinite topology, that is a T1 space. So these were some of the examples of the spaces which are T0 and which are T1 spaces.